Let's start. So today, I hope I can prove two global theorems, the Bonnet-Myers theorem and the Sinji-Weinstein theorem. We'll definitely get through at least 1.5. We might need a little bit of Wednesday to finish. We're going to use the second variation formula. So this, both of these theorems are applications of the second variation formula. It's in the last section of chapter 9. So I'm going to remind you what the second variation formula is. I want to keep it on the board until we use it. And this is a simplified version of it because it's only for smooth variations, and that's all we're going to need today. So remember, if we have a geodesic and a smooth variation of gamma, that means a smooth one parameter family of curves deforming gamma, then this variation has an energy function associated to it, which is just the 1/2 times the integral of the speed squared for each of these curves. And there's an associated variation vector field V, which is a vector field along this geodesic gamma, and it'll be a smooth vector field because this geodesic is a smooth curve, and I'm taking a smooth variation. And the second derivative of the energy at time 0 at s equals 0 was given by this formula. So we have minus the inner product of V with the expression which vanishes for a Jacobi field, and then there was these two extra terms which will vanish for a proper variation. Okay. So in both applications that we'll do today, these will be 0, but we're going to have to explain that. So I've dropped the terms that have, the jumps in V prime because I'm only going to consider variations which are smooth, and so V will have no jumps. Okay, so the first theorem today is the Bonnet-Myers theorem, usually called just Myers theorem. Bonnet proved a weaker version of it with a stronger hypothesis, right? And then Myers improved it. So I'll explain that in the process. So here's the theorem. And then we'll do the corollary, which follows from this theorem. So this is Myers. And the corollary was what Bonnet originally proved, which is simpler. So let M be complete, Riemannian manifold that's complete. And suppose there exists some positive real number R such that Ricci, the Ricci tensor of G applied to V is greater than or equal to n-1 over R squared times G. This is at the Ricci tensor at P, GP VV for all V in TPM. Okay, so the first thing I should say is that in the textbook, if you're looking at it, he doesn't have this 1 over this n-1. He just has a 1 over R squared, and that's because his Ricci was defined to be 1 over n-1 times what everyone else says is Ricci. Right? So this is the right thing with our convention and the standard convention for the Ricci curvature. So what does this say? This says that the smallest eigenvalue of the Ricci as an operator, as a self-adjoint operator, is greater than or equal to n-1 over R squared for all P in M. So what do I mean here? The Ricci is a symmetric bilinear form, but we have an inner product which allows us to identify V and V star, the vector space and its dual, right? The TPM and T star PM. So under that identification, the musical isomorphism, this becomes a self-adjoint linear map. So all the eigenvalues are real, it's orthogonally diagonalizable. And we're saying this condition here says exactly that the smallest eigenvalue is n-1 over R squared. What's the conclusion? Then M is compact, and the diameter of M, which is by definition the supremum over all P and Q in M of the distance from P to Q, is less than or equal to pi times R. Okay, this is the theorem we're going to prove in the first half of the lecture. We start with a mild topological assumption. It's not really a topological assumption, but it's a global assumption. Completeness is a global property. And really, if your manifold is not complete, you can't really expect to say anything. And a curvature assumption, that the Ricci curvature is bounded from below by something strictly positive. Okay? And the conclusion is that the manifold is compact, and we get an explicit bound for the diameter in terms of this number r here. Okay, so if the Ricci curvature was just bounded from below by some strictly positive number, if I just call this thing C, where C is positive, the conclusion holds, right? Because this doesn't matter what positive. I mean, I can write any positive number C as n minus 1 over r squared for some unique positive r. The point is that that r is what shows up here in the diameter estimate. That's why we prefer to write it like this. Okay. Any questions about the statement? Okay, this is a really cool proof. Basically, so the first thing we're going to observe is that it's enough to prove this. So let P and Q be 2 points in M. Since M is complete, there exists a minimizing geodesic. Gamma joining P to Q. We prove this when we prove the Hopf-Rhino theorem, that for a complete Riemannian manifold, any 2 points are there exists a minimizing geodesic between them. There may be more than one. We know, for example, in the sphere, there can be more than one. So it's enough to show that the length of gamma is no bigger than pi times r. Why is this enough? Because then the diameter of M is less than or equal to pi times r. So why is that? Because what is the diameter? It's the supremum of the distance. Since this is a minimizing geodesic between P and Q, the length of this is equal to the distance because it's minimizing, right? So if I can show that for any P and Q, the length is less than or equal to P of r, pi times r, that implies the diameter is less than pi times r. So then M is complete and bounded. And that implies it's compact by the Hopf-Rhino theorem. Right, this is basic metric space theories. In a complete Riemannian manifold, the closed and bounded sets are compact, but the whole space is closed, right? So if it's also bounded, it's compact. So we're reduced to showing that the length of any minimizing geodesic is at most pi times r. Okay, so suppose, for the sake of a contradiction, suppose that the length of gamma is strictly bigger than pi times r. We need to get a contradiction. And we have to use somehow the hypothesis on the Ricci tensor, which we haven't used yet. Okay, so let's call this thing L, because I don't want to keep writing capital L of gamma. Let's let E1 up to En minus 1, and then En, which will be gamma prime over the length of gamma prime, be an orthonormal basis of TPM. Right, gamma is not unit speed because wait, sorry, this should be a 1. I've parameterized it. I've reparameterized it. It's still constant speed because it's geodesic, but I parameterized it like this. So what does this mean? This means that the length of gamma, which I'm calling little l, is the integral from 0 to 1 gamma prime dt, but this is constant speed. So that means that the speed is L. Okay, so this is equal to gamma prime is L times En. Okay, so for k equals 1 up to n minus 1, define a vector field vk along gamma by the following expression. Vk of t is sine of pi t times ek of t. And if you're wondering why on earth would you think of doing this, It's because these are the Jacobi fields for a constant curvature plus one Riemannian metric. So note Vk of 0 is equal to Vk of 1 is 0. So this vector field vanishes at the two endpoints of gamma. So Vk generates a proper variation, which is sigma of S and T is X gamma of T of S Vk of T, call it sigma K, for S in some minus epsilon epsilon and T in 0, 1. And it's a smooth variation because this is clearly smooth. Okay. I should have said sorry, but I'm sorry. Let E1 of T up to En of T be parallel transport of E1 up to En along gamma from P, which is gamma of 0, to gamma of T. Okay. I forgot to say that. Okay, so because parallel transport is an isometry, the E1 of T up to En of T is an orthonormal basis for TPM at every time T. So this is in T gamma of T. And this is, okay, K is fixed here. Okay. And let Ek be the energy function of sigma K. Okay. So we're going to write down the second variation formula for this vector field. I haven't used the Ricci curvature assumption yet, but I will now. So since Ek of T is parallel along gamma, we get that Vk prime is, remember what was Vk? It was sine pi t times Ek. So we get minus pi cos pi t, sorry, plus pi cos pi t times Ek, and Vk double prime is minus pi squared sine pi t Ek t. So by the second variation formula, which is still here, this is a proper variation. So these terms are gone. When we derive the second variation formula, we observe that these terms are 0 for a proper variation. So we're just going to plug in here. We're going to get Ek double prime of 0 is minus the integral from 0 to 1 Vk inner product Vk double prime plus R of Vk gamma prime dt. And this is equal to, let's just write down the definition. This is sine pi t Ek. And then here I get a minus pi squared sine pi t Ek plus the V is going to be a sine pi t. I'm going to factor out. And then I have R of Ek. And remember, gamma prime was L times En. Dt. So here I'm using the fact that gamma prime is L times En. So I can factor out a sine pi t from everywhere, from here and from the right-hand side. So I get a minus 0 to 1 sine squared of pi t. And then what do I have? I have Ek inner product minus pi squared Ek plus L squared R of Ek En dt. And I can write this as minus 0 to 1 sine squared pi t. Using the fact that the EKs are orthonormal, this is a minus pi squared from the first term. And then what do I have from the second term? I have L squared R of EK, EN, EN, EK. Okay, so that's the expression for the second variation formula in this case for this vector field. And now let's take this and sum over all k. So hence, the sum from k equals 1 up to n minus 1 of ek double prime of 0. I'm going to bring the minus sign in. It'll be easier to work with. This is going to be 0 to 1 sine squared pi t. Here I'm going to get, this is just constant, so I'm going to have n minus 1 times pi squared minus L squared times the sum from k equals 1 to n minus 1 r of ek, en, en, ek, dt. Okay, and what is this? If these are orthonormal, right? So if I was summing all the way up to n, it would be Ricci of en, en. But when k equals n, this gives me 0 anyway. So this is equal to the sum from k equals 1 up to n, r of ek, en, en, ek, because the only extra term I've added is 0, which is Ricci of en, en. Okay, so that means that what we have is that the sum from k equals 1 up to n minus 1 ek double prime of 0 is equal to 0 to 1 sine squared pi t n minus 1 pi squared minus L squared Ricci of en, en. Okay, and you can see how Myers thought of what to do, right? Because he stared at the second variation formula and said, what assumption do I have to make on the curvature so I can get, what we want to get is that this is negative, and you'll see why that gives us the answer. So since Ricci of en, en is greater than or equal to n minus 1 over r squared times g of en, en, that's the assumption about the Ricci curvature, and this is a unit vector. So this is n minus 1 over r squared. And the assumption was that the length of this geodesic was bigger than pi r. This gives us L squared is bigger than pi squared r squared. So we get that L squared times Ricci of en, en. Well, this one is greater than or equal to n minus 1 times r squared. And this one is strictly bigger than pi squared r squared. We get that this is strictly bigger than pi squared times n minus 1. Okay, so that means that this is negative, right? Because this guy is strictly negative, and that's non-negative. I'm multiplying a non-negative constant. You can do this integral, right? This is a positive number times something negative. So this is negative. Okay, so the sum of all of these second derivatives is negative. That means at least one of them has to be negative, because if they were all non-negative, the sum would be non-negative. So there exists at least one k between 1 and n minus 1, let's call it k naught, such that the second derivative at k naught is negative. Okay, but this contradicts the fact that gamma is minimizing. Remember, for constant speed curves, the energy, so the length of gamma squared is 2 times L times the energy. what 2 times 1 here. This is parameterized from 0 to 1. This was a little a here, the endpoint of the parameter. So when you're looking at constant speed curves, minimizing the energy is the same thing as minimizing the length, right? And gamma was chosen to be minimizing, so there's no other, and therefore it minimizes the energy because it's constant speed. So there's no other curve nearby which has strictly less energy. But this thing says that it does, right? Because as a function of s, if you look at the energy as a function of s, it has a critical point at s equals 0, E of s, right, ek, and the second derivative is strictly negative, right? So it's a local max. That means if you move a little bit far away, the energy will be less. But it can't be because this is a global minimum of the energy. Okay, does that make sense? Okay, so, it looks very slick when you see that the proof, after many, many years. This might be over 100 years old. My guess is it is over 100 years old. It takes a long time for people to figure out the most efficient way to write it. But basically what happens is that they realize the energy, or equivalently the length, is an interesting functional. They take its first and second derivatives. They look at the second derivative. They see that curvature shows up. And that tells you that if you assume something about curvature and you play with the second variation formula, you may be able to get a conclusion about the manifold, right? And that's exactly what this is. Yeah. Oh, I mean, yeah. So this is a special case of what's called a comparison theorem, right? I showed you that if the Ricci is bigger than or equal to n-1 over r squared, then something happens, right? But there's a more general theorem which says if you have two Riemannian manifolds and the Ricci of one is greater than or equal to the Ricci of the other, then you can conclude something about geodesics and the exponential map and whatever. So what I'm comparing it to really is the constant curvature plus 1 sphere, which has Ricci curvature exactly n-1 over r squared, if it's radius r. So constant curvature r sphere has Ricci n-1 over r squared. And you'll see when I finish this discussion about this theorem that the sphere is exactly the round sphere is exactly the manifold that achieves the diameter bound. You can't do better. So that's where it comes from. Remember, when we talked about the Jacobi fields for constant curvature, we saw this sine pi t. But if you want, the other reason is because there's a v double prime in the second variation formula. So if you pick something where v double prime is going to be a multiple of v, then you can compare. Okay, good. So corollary. So let M G be complete with Ricci of VV greater than or equal to C times G of EV for all V in TPM. So suppose there exists C positive such that then it's the same assumptions as before, right? Because I can always write this as n-1 over r squared. Then the universal cover M tilde of M is compact, and hence pi 1 of M is finite. The fundamental group of M is finite. So, of course, M will also be compact, right? Because I can apply Bonnet-Myers. M is compact, but we're saying that the universal cover of M is also compact. And from there, it follows that the manifold has to be simply connected. So why is this true? So we didn't talk, I don't want to talk too much about covering transformations and universal covers, but so if you don't know this stuff, you can ignore this corollary. But actually, you probably can't ignore it because there's stuff like this on assignment 3 anyway. So let this be the covering map. Call it pi. So what's the covering map? The universal covering map. Right? Given any topological manifold, there exists a unique up to homeomorphism, simply connected topological manifold and a covering map from here to here. Then let G tilde be pi star of G, be the covering metric. You talk about this on assignment 3. Pi is a local isometry. Hence, if Ricci tilde is also greater than or equal to C times G tilde, since this is a local isometry, right? Local isometries basically take curvature to curvature, right? And Ricci curvature to Ricci curvature. So if M has that Ricci curvature estimate, then so will its universal cover. So the Myers theorem, oh, and also, G tilde is complete. This is assignment 3. You show that for the universal cover, not for just the universal cover. Anytime you have a covering map and you pull back the metric on the codomain by the covering map, then this will be complete. So we can apply Myers to M tilde. G tilde tells us that M tilde is compact. But that implies that pi 1 of M is finite because the cardinality of the fundamental group is equal to the number of sheets in the covering. If you have a covering map, then there's a number of sheets in the covering, which doesn't have to be finite, right? But if the covering space is compact, it's very easy to show that any covering map, M is also compact, M also compact. If you have a covering map and both of these are compact, then the number of sheets in the covering has to be finite. So the fundamental group of M has to be finite. So we found out 2 things about complete Riemannian manifolds, which have the property that the Ricci is strictly positive everywhere. Not just strictly positive, but bounded from below by a strictly positive lower bound. That they're compact and they have finite fundamental group. I'm going to show you that you can't relax that in a minute, but let me just do one more corollary. This is the Bonnet theorem. So this is what he proved originally before Myers improved it. Let MG be complete and with sectional curvature K greater than or equal to 1 over R squared for some R positive, then M is compact and the diameter of M is less than or equal to pi times R. And the proof is that this condition, take the trace, implies that the Ricci is greater than or equal to n minus 1 over R squared times G. Okay, so I mean, let's do it. Right? So Ricci of VV.
There it goes. Thanks.
Sydney, is the camera?
No, it's okay now. He moved it.
Okay. Ricci of VV is a sum from k equals 1 to n R of EK V V EK for some orthonormal frame, and that when I can choose my frame here so that E1 up to En minus 1, and then En, which is V over let's do V is an orthonormal frame. So let's suppose here that V is a unit vector. Then this, I'm just showing you why this is true. So this is equal to the sum from k equals 1 up to n minus 1, because I can again, when k equals n, because v is equal to n, this is going to be 0. So this will be just the sectional curvature of the plane spanned by ek and v, and that's going to be greater than or equal to n minus 1 over r squared, because each of them is bigger than 1 over r squared, and I have n minus 1 of them. And that is equal to n minus 1 over r squared g of vv, because v is a unit vector. And then for non-unit vectors, this will just follow because they're both quadratic forms. Okay, so this estimate on the sectional curvature implies this estimate on the Ricci curvature. So when Bonnet proved this, he basically didn't sum over n k over k from k equals 1 to n minus 1 like we did. He just assumed the sectional curvature was bounded by 1 over r squared, and that was enough to give him his conclusion. But what Myers observed was that that's more than you need. This will imply this, right? But this doesn't imply that, right? A lower bound on the Ricci curvature is weaker than a lower bound on the sectional curvature. But this is all you need, because he was able to take this estimate and sum the previous inequalities and get that the sum was negative. So at least one of those terms was negative, and that gave him what he needed. Okay, so that's a typical thing, right? Someone proves something in math, and then someone else comes along and stares at the proof long enough and says, did you really need this assumption? Can you have gotten away with less? And then Myers realized you could have gotten away with less, and that's what he did. Let me make a remark. So the hypothesis that Ricci is bounded from below by a strictly positive multiple of G, well, by a strictly positive lower bound cannot be weakened. So what am I saying here? We assume, i.e., we need some positive C such that Ricci is greater than or equal to C times G. Okay, for it to work. If we just had Ricci is positive for all, this is not enough. So what am I saying here? i.e., if you knew that Ricci of VV was positive for all V not equal to 0, is not enough. There has to be a strictly positive lower bound. So here's an example, and you can check this yourself. If you look at the set of points in R3, where Z is x squared plus y squared, right? This is just the usual paraboloid we show in calculus 3. This is a surface in R3, it's a two-dimensional submanifold of R3 with the induced metric from the Euclidean, right? We take the metric on R3, the flat metric on R3, and we restrict it. Then you can show, let's call this M2. M2 is complete. This is not obvious, right? You have to show this. It's very easy to find the geodesics for a surface of revolution like this, and you can show that it exists for all time. It's complete. It's obviously non-compact. And you can show that Ricci of VV is positive for all V not equal to 0. But what happens is as you go further and further away, Ricci of VV goes to 0 as P goes to infinity. I mean, this is not a precise statement, right? I'm saying if you take points sufficiently far from the center here on this manifold, then you can find non-zero vectors so that when you plug them into the Ricci tensor, you can get something as small as you want, as long as you go far enough away. So the Ricci is always positive as a symmetric bilinear form. It's always positive definite in this example, but the lower bound on the eigenvalues can go to 0 as the points go off to infinity, right? This obviously can't happen with a compact manifold, right? But anyway, the conclusion, this theorem says we start with something complete and we prove that it's compact. So if you're going to get a contradiction involving, the point is, if you had just this, but your manifold was compact, then in fact you do have this for some positive C. But you don't have to do, you don't even need the theorem if you already know your manifold is compact. Okay, so that's one remark, that you really need a strictly positive lower bound on Ricci. And the final remark about this theorem is that the diameter estimate is the best you can do. The diameter estimate is sharp. That means you can't improve it, because if you take Sn with radius r, the sphere of radius r in Rn plus 1 with the round metric, that means I take the Euclidean metric and I restrict it to the sphere of radius r. This has Ricci exactly equal to n minus 1 over r squared times g, and diameter exactly equal to pi r, because the geodesics are exactly those great circles, and the longest geodesic, the largest distance between 2 points in the sphere, is the distance between two antipodal points, and that has exactly length pi times r if it's radius r. Okay? And that's why you see, answering Robert's question, why the sphere is really what's playing the role here, right? This is the first example of a comparison theorem where you're really saying, if you compare the Ricci curvature of your manifold, your unknown manifold, with the Ricci curvature of the sphere, if there's some inequality, then you can exploit the second variation formula to get a conclusion. If they're positive Einstein, yes. So if you have an Einstein manifold where the Einstein constant is positive, then this holds. So you can't have a complete positive Einstein without it being compact. Okay? But of course, if you take away compactness, you can do it, because if I take a compact positive Einstein manifold, remove a point, still positive Einstein, it's no longer complete or compact. Okay. All right, so that was the Bonnet-Myers. The next one, we might be able to do it today, is the Sinji-Weinstein theorem. And again, this is an example. Weinstein is still alive. This is an example of a classical theorem that was later improved in the, I think probably in the 60s or 70s, but it was probably 70s by Weinstein. So I'm gonna state the Weinstein version, and the corollary will be Sinji's theorem. And his proof was, I don't know how he did it. It was a simpler way, probably. Okay, but before I state it, we need a linear algebra lemma, which I think I'm going to write all the way on the far board, because I'm not going to need it until halfway through the proof, and we're going to forget what it is. So I'll write the statement of the lemma down here, and then we'll prove it over there. So the lemma says, let A be an orthogonal
that's
matrix.
not going to show up on the video. It's very dark. You're writing a shadow.
Okay, fine. Okay.
I don't know, maybe if you turn on a light and close that blind, it might show up.
The light is on. I
Oh,
think, yeah, maybe if I close the
well,
blind.
maybe the sunlight is just too bright and the video camera is washing it out. Oh yeah, that's better. Yeah, yeah.
Okay, so lemma. Let A be an orthogonal matrix on Rn minus 1. So it's an n minus 1 by n minus 1 real matrix, whose inverse is equal to its transpose. And suppose that the determinant of A is minus 1 to the n, right? That's just a short way of writing. If n is even, then this is 1, and if n is odd, it's minus 1. Then A leaves invariant a non-zero vector in Rn minus 1. Okay, so what that means is, i.e., it has at least one eigenvalue equal to +1. Okay, so this is a trivial thing to prove. We'll do it now here. There's two different proofs depending on whether n is even or odd. And again, this is an example of Weinstein stared at what Sinji had done and saw, well, how much do we really need? Could we relax the hypotheses? And this is really you'll see when I state the theorem in a minute, why we need this lemma. So the proof of the lemma, well, suppose n is even. If n is even, then n minus 1 is odd. And the determinant of A is +1 because it's minus 1 to the n. So the characteristic polynomial has odd degree. So it has at least one real eigenvalue. Okay, and all the eigenvalues, because it's orthogonal, all the eigenvalues have absolute value 1, right? Even the complex eigenvalues. So the real ones are plus or minus 1. And what do we have? That the determinant of A is the product lambda 1 up to lambda n minus 1. So we have some number because it's a real characteristic polynomial, all the complex eigenvalues come in conjugate pairs. So we'll have some lambda 1 bar, lambda 2 bar, up to say lambda k bar, and then a bunch of minus 1s, and then a bunch of 1s. Okay, well, these multiply together to 1 because they have absolute value 1 and they're conjugates of each other. So all of this, the product of all of these is 1. The product of all of these is 1. And the product of these depends on how many we have. We have an even number here because they come in conjugate pairs, and the degree is odd. Okay, so I can't have, there's an odd number here, and the product is +1, so there has to be an even number of minus 1s. Okay, so there exists at least one +1 eigenvalue. Okay, there might be no minus 1s, but there's an even number of them because the product has to be +1. Yeah, and the determinant is the product of the eigenvalues. I'm just being sloppy because it's so easy, but I shouldn't be sloppy. I'm just saying all the eigenvalues, the complex eigenvalues come in conjugate pairs. That product is 1. All the other eigenvalues are -1 or 1. There's an odd number of them, but there's an even number of minus 1s because the product has to be +1. So that means there's an odd number of 1s. Okay. And the case when n is odd, well, then n minus 1 is even, and the determinant of A is -1 in this case. So you do the same thing, right? You have your conjugate pairs. This is going to give me a +1. And now we have an even number. So we have some -1s and some +1s. So there's an even number of real eigenvalues. So there exists at least one pair of Because why there has to be at least one? Because if there were no real eigenvalues, the determinant would be +1, but it's -1. So there exists at least one pair of real eigenvalues. There's an even number of them, and it can't be 0. It has to be at least 2. And at least one of those, of which is +1. Because if in each pair they were both -1s, then the product would be 1, but it's -1. Okay, so there's at least one eigenvalue of +1. Okay, this is trivial, as I said, trivial linear algebra, but we're going to use it in the middle of the proof, which I think we'll have time to do. And I'll state when I state the theorem, well, let me state the theorem now, the Weinstein theorem, and we'll see exactly where this issue comes up. I think I'm going to state it on this board so I can keep this board on as long as possible. So this is the Weinstein theorem. Let M be a compact, oriented, n-dimensional Riemannian manifold with positive sectional curvature. That means for any point in M and any two-dimensional subspace of the tangent space, the sectional curvature at that point of that two-dimensional subspace is positive. Because the manifold is compact, in fact, you can show that there's some constant so that k of LP is greater than or equal to C, which is positive for all LP. Okay, because it's compact. Because there's going to be it's a continuous function on a compact space. The space of all two-dimensional planes on M, if M is compact, is a compact space itself, where a continuous function has a positive lower bound. But that's not going to be important here. So then let F be an isometry such that F preserves orientation if n is even, and it reverses orientation if n is odd. Then F has a fixed point. I.e., there exists some point, at least one point in M, such that F of P equals P. Okay, this is what we want to prove for the rest of the lecture.
What's the
yep.
assumption on M prime? I mean, obviously it has to be orientable.
There's no M prime. There's no M prime.
Oh, what's that? Oh, I see. It's sorry.
Yeah. Yeah. So there's one manifold. It's compact, oriented, and positive sectional curvature. And we say that any isometry on it, well, it has to be orientation preserving in the even dimensional case and orientation reversing in the odd dimensional case. It has to have a fixed point. So the original Sinji theorem was in the even dimensional case, right? So he had this theorem where M was even dimensional, compact, oriented, positive sectional, preserves orientation. The isometry has to have a fixed point. And Weinstein examined the proof and realized, well, if n was not even, it would still work as long as the isometry reversed the orientation. Right? That's why you have these two assumptions. Okay, so this is a cool proof. I have half an hour. I think I can prove this. We probably won't get to the corollaries and the application, well, the corollaries basically until Wednesday, but I think I can prove this theorem. There's a lot of nice ideas that go into this proof. So we want to prove that this isometry has a fixed point. Okay, we're going to suppose it doesn't. Then for every point P, f of P is not equal to P. So suppose f has no fixed points. Then for all Q and M, f of Q is not equal to Q. So the distance from Q to f of Q is positive. Okay. Hence the function that sends Q to the distance from Q to f of Q has a positive global minimum. Right? Because f is continuous, it's an isometry, it's smooth. The distance function for any metric space is continuous. So this function, which takes Q to D of Q comma f of Q, is continuous, and M is compact. Right? It's continuous, and the manifold is compact, so it has a global minimum. That global minimum can't be 0 because this function is positive everywhere. Okay. So let P be a point in M where D of P, F of P is the global minimum. Right? There might be more than one such P, but there exists at least one, and that global minimum is positive. And let's let gamma from 0L to M be a normalized, so unit speed, normalized minimizing geodesic joining P to Q, joining P to F of P. Okay, so, and this exists because M is complete. It's complete because it's compact, right? Any compact Riemannian manifold is complete, and therefore any 2 points can be joined by a minimizing geodesic. So this means that gamma of 0 is P, gamma of L is F of P, L is the distance from P to F of P, and gamma prime of T is 1 for all T. Okay. So I'm going to draw a picture. There's P, F of P. This is gamma, gamma prime of 0, gamma prime of L. Let's let capital P be parallel transport along gamma from F of P, which is gamma of L, to P, which is gamma of 0. So capital P goes from TPM, TF of PM to TPM, and it's an isometry. Parallel transport is an isometry. Okay. We also have the push forward of little f at the point P. This goes from TPM to TF of PM, and this is also an isometry, right? Because f is an isometry. So therefore, let's let A tilde, I'm calling this one A tilde because there's going to be something else that's going to be A. Let A tilde be the composition of these two. This goes from TPM to TPM, and it's an isometry. Composition of isometries is an isometry, and this is an isometry on TPM, right? So the first thing I do is I apply the push forward of F, which goes from here to here, and then I do parallel transport back along gamma to end up back at TPM. So I claim that F compose gamma prime at 0 is equal to gamma prime of L in T f of Pm. Okay, so let's make sure that this makes sense. Gamma prime of L is in this picture here. It's in T f of Pm. And where does this live? By definition of the push forward, this is also in T f of Pm. This is applying f star P to gamma prime of 0. So
Comment.
I have gamma prime. Yeah.
Do you also have to assume that the manifold is connected?
Oh, I think I made a blanket assumption at some point that because the manifolds are always going to be connected from now on, quite a while ago.
Okay.
Yeah. Yes. Of course, whenever I say given any 2 points there's a geodesic between them, this is always connected. Okay, so I want to show that these two vectors, the green and the red here, are the same. That's this claim. Okay. So let's prove this claim. If I look at the map F compose gamma from 0L to M, this is a geodesic, since M is an isometry, since F is an isometry. You proved on an earlier assignment that isometries take geodesics to geodesics. And F compose gamma of P is of 0, sorry, is F of gamma of 0 is F of P, and F compose gamma of L is F of gamma L, which is F of P, which I'll just call F squared of P for shorthand. So let's draw this picture again. This is P, this is F of P. I have gamma joining those two, and then F squared of P. Remember, there's no fixed points. That's our hypothesis. So then F compose gamma is a geodesic from F of P to F squared of P. Let's let T prime be some time strictly between 0 and L. So this is this is gamma of T prime. And this is going to be F compose gamma of T prime. I want to prove this claim. I want to introduce some more notation here. I'm going to call P prime is gamma of T prime. And F of P prime is F compose gamma of T prime. Right. So this is F compose gamma. So since gamma of T prime is P prime, this is P prime. This is F of P prime. Okay. So this is a nice argument. Since F is an isometry, we know that the distance from P to P prime is the same as the distance from F of P to F of P prime. Okay, so the distance from P prime to F of P prime by the triangle inequality is less than or equal to the distance from P prime to F of P plus the distance from F of P to F of P prime. Right, that's just the triangle inequality. But now I'm going to use equation 1. This is equal to d of P prime F of P plus d of P prime P. But this is equal to the distance from P to F of P, since gamma is a minimizing geodesic. From P to F of P. Right? What is this? This is always what do I want to say? Right, since gamma is minimizing from P to f of P, then any proper subsegment of gamma will be minimizing between its endpoints, because if it wasn't, if let's say gamma restricted to here wasn't minimizing from P to P prime, then I can modify it to get a smaller curve from P to P prime. But that means I can take that modification plus this to get a smaller curve from P to f of P, and I can't, because this geodesic is minimizing from P to f of P. Therefore, this geodesic is minimizing from P to P prime, and this geodesic is minimizing from P prime to f of P. So the distance from P to P prime is the length of this, and the distance from P prime to f of P is the length of this. So the sum of those two distances is the length of this thing, which is the distance from P to f of P. So that's why we have this equality here. Okay. I've used the fact that f is an isometry, and I've used the fact that gamma is minimizing from P to f of P. But now I've shown that this is less than or equal to this distance. But P was chosen to achieve the global minimum of the function Q goes to D of Q f of Q. But P is where the global min of Q goes to D of Q f of Q is attained. And I found another point where the distance from P prime to f of P prime is less than or equal to that. So they have to be equal. So D of P prime f of P prime is equal to D of P f of P. And hence, we have equality in the triangle inequality. Okay, so therefore, I don't need this picture anymore. So what does that mean? So if we look at the combination of this curve from P to f of P, followed by this curve from f of P to f squared of P, it's a geodesic, because each of them is geodesic, and it's length minimizing. So let me say it here. So the curve, which goes from P to f of P along gamma, and then to f squared of P along f composed gamma, is a geodesic, since it is length minimizing from P prime, which is gamma of T prime, to f of P prime, which is f composed gamma of T prime, for all T prime between 0 and L. Right? We just showed that the distance from P prime to f of P prime is equal to this distance from here to here and here to here. That's what the equality in the triangle inequality says. This distance is equal to, we know what this distance is because gamma is a minimizing geodesic from P to P prime. So this is just the length of gamma from gamma of T prime to gamma of L. And again, this one is also, because f is an isometry, it doesn't just take geodesics to geodesics, it takes minimizing geodesics to minimizing geodesics. So this is the length of f composed gamma from f composed gamma at time 0 to f composed gamma at time T prime. Okay, so the fact that we've shown that there's an equality here is what says that this composition of these two, not a composition, concatenation of this curve followed by this curve, minimizes the distance between any point, any 2 point. We already know that gamma minimizes the distance between any 2 points on gamma, and f composed gamma minimizes the distance between any 2 composed points on f composed gamma. But what we showed here now is that from any point P prime inside here to its image point f of P prime, this pair of these two curves achieves the minimum distance from here to here. But then we know from earlier in the course that if we have a curve, which is piecewise smooth a priori, piecewise smooth, which achieves a minimum distance, it has to be a geodesic. So it's regular, so it's not broken. Right? So this curve is not, is smooth. So it's not broken. The velocity doesn't jump at f of p. Hence, gamma prime at L is equal to f compose gamma prime at 0. This proves the claim. Right, so the picture is there is no jump here. So the velocity of the green curve at the endpoint is the same as the velocity of the red curve at the initial point. That was the claim. The claim has just disappeared from the board, but this was the claim. And now we've long forgotten what A tilde is. So let me remind you what A tilde is. Recall A tilde was a linear isometry on TPM, was defined to be parallel transport compose F star P. Okay, so let's see what this A tilde does. A tilde applied to gamma prime of 0 is going to be P applied to F star P gamma prime of 0. But that's P applied to F compose gamma prime at 0. That's just the definition of the push forward. And now by the claim, F compose gamma prime at 0 is gamma prime at L. But then this has to be gamma prime of 0 because parallel transport is unique, right? The velocity vector field of a geodesic is parallel along gamma. And so if you parallel transport gamma prime of 0 along gamma to gamma of L, you're going to get gamma prime of L. And this was the parallel transport in the opposite order. So this map A tilde, which is an isometry, we've just shown that it preserves gamma prime of 0. That's why we had to work so hard to get this claim. Okay, we have this isometry that's built out of parallel transport and F. Oops, I don't want to erase that. And it preserves gamma prime of 0. And it's an isometry, therefore it's going to preserve the orthogonal complement. So let's let gamma prime 0 perp be the orthogonal complement of the span of gamma prime of 0. So this space is n-1 dimensional. Okay, and let A be the restriction of A tilde to this orthogonal complement. And what we just showed, well, because A is an isometry and it preserves gamma prime of 0, it has to preserve the orthogonal complement. Because A tilde is an isometry and it preserves gamma prime of 0. It has to take the orthogonal complement to the orthogonal complement. And so A is an isometry on an n-1 dimensional inner product space. Which is this guy. And moreover, parallel transport always preserves the orientation. Moreover, parallel transport P preserves orientation. I don't remember if I ever said this when we talked about parallel transport, but it's easy to see that parallel transport preserves orientation because you basically the parallel transport from some time 0 to some time t is continuous in T, and at time 0, it's the identity. So it has to preserve orientation at time 0, and it can't jump because it's continuous. So it preserves orientation everywhere. So hence, the determinant of A is equal to the determinant of A tilde. This is because A tilde restricted to the span of gamma prime of 0 is the identity on the span of gamma prime of 0, right? It takes gamma prime of 0 to itself. So that is an eigenvector with eigenvalue 1, and the orthogonal complement has some eigenvectors which you multiply to get the determinant. So this is why this is the same, because the only extra eigenvalue here is 1, but this is equal to the determinant of P times F star P. That's the definition of A tilde. And then the determinant of the product is the product of the determinants, but the determinant of capital P is 1 because it's preserving orientation. So this is equal to the determinant of F star P, which is -1 to the n, because the hypothesis of the theorem is that F preserves orientation for n even and reverses for n odd, right? If we go back to the statement here of the Weinstein theorem, this is where we're finally using this. So what do I have? I have an orthogonal transformation on an n-1 dimensional. I have an isometry on an n-1 dimensional vector space, which preserves orientation when n is even, reverses when n is odd. So the determinant is -1 to the n. So by the lemma, A tilde, A has a fixed point. Okay. Let's see. Can I finish? I might be able to finish. 8 minutes. So we had to work very, very hard to get that this map A has a fixed point. I don't need the statement of the theorem anymore, and I don't need the lemma anymore. Remember, we want to find a contradiction. And I haven't used yet the positive sectional curvature, because I haven't used the second variation formula yet. So there exists some E1 in TPM with E1 orthogonal to gamma prime of 0, such that A of E1 equals E1. That's exactly what this fixed point theorem, sorry. By the lemma, A leaves a non-zero vector invariant. It's the same thing, but let's write it more precisely, right? Because A is a linear map on a vector space, and we proved that it has an eigenvalue equal to +1. So it has a non-zero vector that it preserves. Let's let E1 of T be parallel transport of E1 along gamma. So because parallel transport is an isometry, E1 and gamma prime are orthogonal at time 0. They're orthogonal for all times. Okay. It's not going to happen. I got to find a good place to stop and finish on Wednesday. Okay, I'm gonna do 3 more minutes, and then I'll start from there on Wednesday. So let's let beta S goes to beta of S for S in some minus epsilon epsilon be a geodesic with beta of 0 is P and beta prime of 0 is this E1, which is orthogonal to gamma prime. So the picture here, this was our geodesic gamma, which goes from P to F of P. And this is gamma prime at 0. This is gamma prime at L. And we found this vector E1, which is fixed by A. And this is E1 at L, right? It's orthogonal. E1 of T is orthogonal to gamma prime of T for all T. And then beta, running out of colors, green. I've already used, anyway, this is beta. Beta is a geodesic passing through P, but with initial velocity E1. Okay. So let's use the fact, because this will be a good place to stop, and I can just remind you where we were on Wednesday. Let's use the fact that A preserves E1 so that we don't have to worry about that again. So A of E1 is E1. What does this say? This says that P composed F star at little p of E1 at time 0 is E1 at time 0. Okay. But this is parallel transport, remember, from gamma of L back along gamma. And E1 of T is parallel. So this tells us that F star P of E1 at 0 is equal to E1 at L, since E1 of T is parallel along gamma, and parallel transport is unique. Okay, so this is where I've used the fact that A preserves E1, but hence F composed beta, this is also a geodesic, because F is an isometry. And what do we know? We know that F composed beta at time 0 is F of beta of 0 is F of P. And F composed beta prime at 0 is F star P beta prime 0. That's F star P of E1 at 0. And we just proved that that's E1 at L. Okay, so I can finish the picture and say that the geodesic passing through F of P with initial, the geodesic F composed beta passes through F of P, and it has initial velocity E1 at L. So on Wednesday, I can restate the theorem and say we've reduced it to this case, right? We know that P and F of P, that this gamma is a minimizing geodesic between P and F of P. And then we've proven that there's some orthogonal vector E1 to gamma prime of 0 that we can parallel transport along here that's invariant under A, but that really just means that if we look at this geodesic beta through P with initial velocity E1, then F composed beta will be a geodesic through F of P with initial velocity E1 of L. So this parallel vector field E1 is what we're going to use as our essentially as our variation for the second variation formula. Let me just make sure that's correct. Yeah, essentially we're going to use that as our variation. So we'll continue next time. I didn't finish it, but this is a good place to stop because we don't have to worry about that linear algebra lemma again, and we don't have to worry about this map A and A tilde again. I can just tell you we've proven that there exists this E1 that when you parallel transport it along here, this geodesic, the geodesic beta with initial velocity E1 is taken to the geodesic F composed beta with initial velocity E1 of L. Okay, and from there we'll finish it. We haven't used the positive sectional curvature yet, but we have used compactness, We've used that F is orientation preserving when n is even, F is orientation reversing when n is odd. That was it, I think, right? So the only thing left to use is the positive sectional curvature assumption. And what we want to do is get a contradiction, right? And we're going to use the second variation formula to get our contradiction. And once we do that, so I just need another 10 minutes to finish the proof. Then we'll look at a couple of corollaries of this theorem. And then we'll be done with chapter 9, and we'll move on to the Rauch comparison theorem after that. Okay, so when we continue on Wednesday, I'll rewrite the statement. And I'll remind you, this is where we got to. We want to get our contradiction, but we don't need any of those other things anymore, except the positive sectional curvature. We've used everything else.